In this video, we are going to discuss on tutorial 19. Okay, the topic is molecular speed distribution, degree of freedom, law of accretion of energy, and internal energy. Okay, question 1. 6 molecules of a gas move with speeds of 450 meter per second, 400 meter per second, 500 meter per second, 550 meter per second, 450 meter per second, 500 meter per second. Calculate the mean speed and the root mean square speed of the molecules. Okay, for the mean speed, we total all the speed divided by 6, so we get 475 meter per second. For root mean square speed, so the formula is square root of 450, all the speed squared, and we total them up divided by the number of the speed, which is 6. So the answer is 477 meter per second. Okay, next we go to question 2. Okay, A. Sketch the molecular speed distribution graphs for a sample of gas at 300 Kelvin and at 500 Kelvin, and then mark the most probable speed at 300 Kelvin as V naught and as and at 500 Kelvin as V naught prime. Then use the graphs to compare the number of molecules with speeds greater than the most probable speed at 300 Kelvin and 500 Kelvin. Okay, question A. So we draw the graph, number of molecules against speed. Okay, so this is the shape of the graph for 300 Kelvin. And another molecular speed distribution graph is for 500 Kelvin. Okay, so compare these two. Then label with V naught for most probable speed. So the highest or the peak here is the largest number of molecules reading on the y-axis. So that's mean down here reading from the x-axis will be V naught. Okay, or V peak. The most probable speed V naught. Okay, so for graph 500 Kelvin will be here. Okay, so the question asks to label with V naught prime. Okay, that's the answer. Now we go to question B. Then use the graph to compare the number of molecules with speed greater than the most probable speed at 300 Kelvin and 500 Kelvin. Okay, so for the number of molecules can be represented by the area under the graph. Okay, this is for 300 Kelvin. So at 300 Kelvin, area A1 represents number of molecules with speed larger than V naught. Okay, larger than V naught. For 500 Kelvin distribution, molecular speed distribution, so the shaded region is the purple shaded region. So this will represent the A2 here, area 2 or A2 represent number of molecules with speed larger than V naught prime. So compare these two. Okay, A2, you see here A2 is larger than A1. Okay, area 2 is larger than area 1. This means that the number of molecules with speed larger than V naught is less than a number of molecules with speed larger than V naught prime. Okay, next we go to question 3. So which of the following influences the degree of freedom of a gas molecule? So the answer is A. So the number of atoms per molecule and the temperature of the gas. Okay, so F, degree of freedom, depends on whether the molecule is monoatomic, diatomic or polyatomic, and F is greater at high temperatures. Okay, next, question 4. Find the energy of the following gas molecules at 300 Kelvin. Okay, for oxygen gas, for helium, and for carbon dioxide molecule gas. Okay, so the formula for the energy, we use half FKT. F is the degree of freedom. So the oxygen molecule, because O2 here, so this is a diatomic. So that means the F is 5, right? Degree of freedom is 5. So we substitute the equation into this equation 5. Okay, K is the Boltzmann constant and temperature 300 Kelvin. So we get the energy is 1.04 times 10 to the power of negative 20 joule. Okay, for helium gas, this is a molecule. The molecule is monoatomic, so the F value is 3. So using the same formula, so the energy for helium is half times 3 times Boltzmann constant times 300. So we get 6.21 times 10 to the power of negative 21 joule. So make sure you label with E, subscript helium to see to distinguish between just EO for E oxygen, energy of the oxygen. So for B we label with E helium, and for C we label E carbon dioxide. So carbon dioxide is polyatomic because we have carbon molecule and oxygen molecule too. So this is polyatomic. So the F degree of freedom is 6. So you substitute into the equation here and we get the answer 1.24 times 10 to the power of negative 20 joule. So there is a mistake here. So you change this to CO2. Okay. Okay, next we go to question 5. Okay, a vessel contains 2 moles of helium gas and 1 mole of hydrogen gas at 350 Kelvin. The mixture is heated at constant volume to 400 Kelvin. Calculate the total energy of the mixture at 350 Kelvin and at 400 Kelvin. Okay, for question A, so formula for the internal energy is half NFRT. Okay, so the U total, we have 2 molecule gas, so that's mean U helium plus U hydrogen. Okay, so you substitute the F, the N, number of moles, okay, there 2 moles, and then the F is depends on what type of the gas. So helium is a monoatomic, so 3, the F is 3. R is a molar gas constant 8.31. So temperature 350 Kelvin. And for hydrogen is a diatomic, so F is 5. And the number of moles for hydrogen gas, this hydrogen gas is 1 mole. Okay, so the answer is this one. Hydrogen is diatomic, helium is monoatomic, F3. So diatomic means F5. Okay, so the answer is 1.60 times 10 to the power of 4 joule. Okay, so for at 400 Kelvin, so the same formula, only that we replace this temperature with 400 Kelvin. Okay, then the answer is 1.83 times 10 to the power of 4 joule. Okay, next we go to question 6. A tank contains 700 meter cube of neon at a pressure of 1.01 times 10 to the power of 5 Pascal. The temperature is changed from 293 Kelvin to 294 Kelvin. What is the change in the internal energy of the neon? Okay, so the internal energy formula, half NFRT. So for N, we can calculate using PV equals to nRT. So we are going to use 2 formula here. Okay, so for number of moles N, so N equals to PV over RT. So substitute the pressure 1.01 times 10 to the power 5. Volume is 700 meter cube. R is 8.31, molar gas constant, and temperature is 293 Kelvin. Okay, So the answer for N is 29036.93 mole. So this is N. So you can so this is at initial 700. So we will use temperatures here 293 for N. So at temperature 294, the N also will be the same. Okay, N will be the same. Only the pressure change. The pressure uh, the pressure change, or the volume change. So depends what kind of we fix the temperature change. So that's mean the P and V change. Temperature change. So that's mean for 293 700 and the pressure given. Okay, now we use this N into the equation here. Okay, so the internal energy, change in internal energy means final minus initial. So half NFR is constant, we factor out. So bracket we write final temperature minus initial temperature. Okay, so you substitute the N that we calculate just now, and then the F is 3. Why 3? Because neon is a monoatomic, and then the R is 8.31. Okay, so we substitute into here, and temperature final minus initial, so 294 minus 293. So the answer is 3.62 times 10 to the power of 5 joule. Okay, next okay, that's all for the tutorial 19, and bye bye.